Click the bell icon to get latest videos from Ekeeda.
Hello friends, I welcome you all to this video. We are with the microwave resonators to learn the subject microwave engineering. So as in the previous video we have dealt with the series resonant circuit, because as we know whatever the microwave resonators we shall be having possible for the microwave engineering applications, they have very similar operations with respect to the resonant circuitries that we have obtained with the help of lumped elements. So therefore it was the series resonant condition we have derived the expression for the input impedance there, and the resonance frequency was also shown, and the comparison with respect to the half power beam width that can be for the Z in with respect to the frequency range we have represented there. So let us have the another resonant circuitry that is possible with the connections from the lumped elements, and that it is the parallel resonant circuits. So let us begin with. So here we have the parallel resonant circuit, our topic. So as the lumped element into the previous video we have been used there the capital R, the resistor component, the capital L, the inductor component, and the capacitor represented by capital C. So these are the three lumped elements. So we had there first of all the series connection there. So the components were arranged one after another, and finally the complete branch was supplied with the potential capital V to have the flow of current capital I through it, and the corresponding analysis to have formulations for the input impedance we had. Now we are not going to have the components arranged one after another, but the branches individual for the resistor, inductor and capacitor are parallel, and to the common point of all these parallel branches we shall be having a supply V, and let us have the further analysis. So such a parallel connection with respect to the lumped elements R, L and C we show in this schematic diagram. So in this diagram, as this is the supply that we show here, so there it is a potential capital V across these two nodes here. So it has been provided further to the individual branches, those are parallel, corresponding to the resistor component capital R, the inductor component capital L and the capacitor component capital C here. So I can say here the common point that these individual branches that have been in parallel have been now supplied with the potential capital V, and through this branch we have the flow of current denoted by capital I here. So to such a parallel connection of RLC, the corresponding input impedance can be marked onto this circuit diagram by Z suffix IN here. Further, the representation of the input impedance can be into the mathematical form. So we write the equation for input impedance Z suffix IN. So this is equal to, in the bracket that we are going to have inverse, the first component will be 1 upon capital R, added to we have 1 upon j omega L here for the inductor component. Further it is added to j omega C here. I make the inverse here. So basically into the parallel connection, whatever the resultant component parameter measured is, so it is 1 upon Z in, it should be, it is equal to this much. So I take the inverse of the right hand side. So let this representation of the input impedance required is by equation number 1. Now as we have the input impedance expressed for the parallel circuitry for RL and C here, now let us have the representation for the complex form of the power that has been delivered to this resonant circuit. So it is by P suffix IN. So P suffix IN can be 1 by 2 times the voltage in multiplication to the complex representation of the current I here, which can further also be expressed with the help of the input impedance Z in. So I write 1 by 2 times Z in multiplication to mod I, which is squared here. Or we can also have the representation in terms of 1 by 2 times mod V squared here in multiplication to 1 upon Z in asterisk to represent the complex conjugate representation here. Whereas finally we can carry the P suffix in is equal to 1 by 2 mod V squared in multiplication to the bracket that has involved the representation of the lumped elements R, L and C. So here we have 1 upon R added to J divided by omega L minus J times omega C here. So let this can be the next equation number, equation 2 it is. So after expressing whatever the average input power has been delivered to the parallel circuitry of RLC, let us account for what are the power losses. So for the power that has been dissipated by the pure resistance component capital R, we can express P suffix loss. So it is equal to 1 by 2 times mod V, that is squared, and it is divided by R here. So this is the first kind of dissipation, and we represent in continuation of the equation 3, and it is part A, let us say. Next to the power dissipations due to the resistor component R, let us account for the another two components in the parallel connection, the inductor and the capacitor here. As we know that the capacitor will be having a storage of the electric energy here. So the average amount of the electric energy that has been stored into the capacitor component, so it will be represented by W suffix E and given in the form of 1 by 4 times mod V squared in multiplication to the capacitance value C. So let this can be the next part of the equation number 3. It is 3b here. So we have dealt with the resistor component, the capacitor component into the parallel resonant circuitry. Now we are left with the inductor component. So the inductor component will be associated with the magnetic type of the energy. So the magnetic type of the average energy stored into the inductor component can be denoted by W suffix m, and it is given in the mathematical form by the equation W suffix m is equal to 1 by 4 times mod of capital IL squared in multiplication to the inductance value capital N. So this can also be expressed using the frequency component. So it is 1 by 4 mod V squared in multiplication to 1 upon omega square L. So let this can be the equation number 3c here. So in this equation, instead of representing the capital I incomplete, we have represented I suffix L here. So this is the amount of current flowing through the individual branch of the inductor component only. Now the complex form of the power that we have represented into the earlier equation can be rewritten into the form using the previous A, B and C parts of equation number 3. So this is P suffix in is equal to P loss added to twice of J omega in multiplication to the difference of energies W suffix m minus W suffix E corresponding to the magnetic and electric stored energies there. So let this equation I number equation number 4. So this is also to the identical form that we have discussed in the case of series resonant circuitries there. Now in the similar fashion, we can express the input impedance by using the 3 parts of equation number 3. So I represent Z suffix in, the input impedance is equal to twice of P in divided by mod I, which is squared here. So expressing it into the P loss added to twice of J omega in the bracket W suffix m minus W suffix e, which is divided by 1 by 2 times these two, we get to the denominator shifted, mod I, which is squared here. So let this can be the new equation number 5 here. So we have the representation of the complex form of the power delivered to the parallel circuitry of the lumped elements, as well as the input impedance is mentioned here. So as discussed into the previous topic also, that it was the series resonant circuit, and now we are dealing with the parallel resonant circuit. The resonance condition occurs when we have the stored amount of energies into the magnetic and the electric forms to be equal. So the condition was expressed to be W suffix m is equal to W suffix e. So in that situation, the equation number 5 and equation number 3a, if we use the input impedance Z suffix in, can be expressed by the form we have P loss divided by 1 by 2 times mod I, which is squared here. So this is equal to capital R here. So capital R, that is a component into the Z input here, will be a pure form of the real impedance here, or real part we can say here. Next to that, from the equations 3b and equation 3c here, we can use again the condition, the stored energies of magnetic and electric form to be the same here. The resonant frequency expressed in the representation omega suffix 0, given as 1 upon under root LC here. So this is the resonant frequency for the parallel resonant circuit expressed by equation number 6, and this is very similar to that of the resonant frequency we have obtained in the case of series resonant circuit also. So for the differential purpose here, the resonant frequency we have expressed here for the parallel resonant circuit is also mentioned to be the anti-resonance frequency. Now let us address the quality factor associated with the parallel circuitry for the resonance by use of R, L and C components here. So the quality factor in general we represent capital Q. The definition we have already made into the previous topic also, that the angular frequency omega in multiplication to the average amount of energy stored divided by the energy that has been dissipated per unit cycle here. So if we discard the connections to the external circuitries with the loading effect, so that time the Q factor is denoted by Q suffix 0 and it is called as unloaded quality factor. So if we compute the unloaded quality factor for the parallel resonant circuitry made up by the RLC components, so it is expressed as in terms of the resonance frequency omega 0 in multiplication to the ratio of twice W suffix m divided by P loss here. So here we can express it to the form capital R divided by omega 0 into L, or omega 0 into R into C also. This can be given by equation number 7 here. Now if you observe the final relationship with the unloaded quality factor with that of the capital R here, we come to see that for the parallel resonance circuit with the increase into the capital R, we get the increase into the unloaded quality factor. So both are directly proportional to each other. So now at the near resonance condition, let us have simplification of the expression for the input impedance. So for that case, we can make the use of series expansion results there. The series expansion can be represented as 1 upon 1 plus x approximated to the series of 1 minus x added to the other forms that we know here. So now let us have the assumption that the generalized frequency angular omega is expressed as the resonant frequency omega 0 added to delta omega, where delta omega is of the small amount in consideration. So this gives the approximation of input impedance Zin equal to the form we have 1 by r, this is added to 1 minus I have the delta omega that has been divided by the resonant frequency omega 0 in the angular form. This is all divided by G times omega 0 times the inductance value capital L here. Next to that, we have the third term that has been written as J times omega 0 into capital C, and the last term J times delta omega into capital C here. So this is all into the inverse here. The further simplification to this approximation, we can make it to the form, in the bracket we have 1 by r component added to J times delta omega divided by omega 0 square L added to the third term we have the last one, that it is J times delta omega into capital C. The bracket is completed and the power inverse is kept as it is. We can simplify this step next to more approximations. So Zin is equal to, we have 1 by r added to twice of J in multiplication to delta omega capital C. Here it is inverse. And finally, we can approximate it to the form, we have r divided by 1 plus twice J times delta omega in multiplication to RC here. So therefore, we can express finally Zin is equal to capital R divided by 1 plus twice J delta omega by omega 0 into the unloaded quality factor, that it is represented Q suffix 0 here. So let this form of the input impedance Zin is given equation number 8, where we have the resonant frequency omega 0 square is equal to 1 upon LC, we can write here. So omega 0 square is equal to 1 upon capital LC. So when we have r value to be the infinity, the above equation reduces to the form Zin, the input impedance, is equal to 1 divided by J times twice C in the bracket omega minus omega 0, the resonant frequency here. Now when we replace the simple form of omega 0 by the complex form representing the lossless condition omega 0 in the bracket 1 plus J divided by twice of Q0 here, that can be equation number 9, which can be accounting the effect of losses there. So this is the same case that we have done in the previous topic, that it is series resonant circuit also. Now let us have a look onto the schematic diagram. It is basically a graph here. So on this graph we have the marking corresponding to the magnitude and the frequency values for the input impedance here. So here we take mod of Zin as a function of omega, the magnitude here, whereas on this axis we take omega 0, the resonant condition, intersecting into the 0 here, the origin. This is the marking of 1, the value of frequency, where we have the peak value obtained for the corresponding input impedance here. So this peak is having at the value capital R, whereas the half power beam width, what we talk about, is basically 0.707 times the value of R. Hence this is the value, the range of frequencies I can say for the corresponding two markings, that it is the bandwidth here. So it is for the half power here. So the half power is achieved at this particular level. So corresponding to the representation into the graph there, we can denote mod of Zin to be squared. It is given as r square divided by 2. So this implies to the bandwidth represented by BW, it is equal to 1 upon Q0, the unloaded quality factor. So here we are going to conclude the topic parallel resonant circuit. I hope the understanding corresponding to how the series resonant circuitries and the parallel resonant circuitries can lead to the further resonance there. So we shall be adding some more information with respect to the loading and unloading conditions for the quality factor by the next lecture, and will continue in the same unit there. So I hope for more information, if you want to have for microwave engineering topics, you will surely subscribe to Ekeeda channel. Thank you.